Okay, for number 32, this is a part 3 question. Usually constructions are part 2 questions, but once in a while they'll make it a part 3, which means that it's 4 points. So it starts with a construction, and then you're going to see that there's an additional question at the end so that we get up to 4 points. All right, 32, triangle ABC is shown below. Using a compass and straight edge, construct the dilation of triangle ABC, centered at B, with a scale factor of 2. So we need this triangle, each side of the triangle, to double in length if we have a scale factor of 2. So what I'm going to do, I just like to bold any points, any vertices before I start my construction so it's easier to see. I'm just going to bold those 3 points. If it's centered at B, this means that this is a fixed point. We don't want to change point B. But what we're going to do, if you look at how I'm tracing over BA, I'm going to find A prime, which is probably going to be somewhere over here. Okay. If I'm tracing over BC, I'm going to find C prime, which is probably somewhere over here. And then when I connect, I'm going to have my triangle that's been dilated. So let's measure how big BA is. B is our fixed point, this gold ring of my compass. And if you're using a regular compass, that's fine too. I'm going to put that on B, and I'm going to find the letter on my compass that lines up exactly with A. If you're using a safety compass like me, keep in mind that these measurements are slightly different than the others. So if something here looks close but not great, okay, you can go back and forth and kind of try and check. Okay, so to me, this one here looks the best, the one that's like right by G. And if you want, you could put like a little note there to remind yourself. Okay, now I'm going to move the compass up here. I'm going to use that same hole in the compass. So I'm going to use G again. Make an arc, and then using my compass as a straight edge, here's my new point. So this is like my A prime. Okay. All right, let's repeat that same process for BC. Gold ring on B, our starting point. I'm going to find the letter on my compass that lines up exactly with C. That's basically how we measure things without a ruler. And this one looks really good, the one right before S. So again, if you think you're going to forget, you could just jot it down. Move the gold ring of your compass to C. Use S again. And we're going to use now the compass as a straight edge to connect. So when you are dilating, the sides are parallel to one another, so we're not rotating anything. That's how I know just to kind of connect here. And this is our C prime, by the way. And now let's use the straight edge part of our compass one more time. I'm going to connect A prime and C prime. And now I have successfully dilated my triangle by a scale factor of 2. The side lengths were doubled. And it was centered at B, meaning B did not change. Now I mentioned before, this is a 4-point question, so there's an extra component here. It says, is the image of triangle ABC similar to the original triangle, and explain why? So first of all, the answer is definitely yes, and we can talk about a few different things you could write here, but I'm going to start off with saying yes, the triangles are similar. Now let's explain why. We're not going to get credit if we just say yes. We have to attempt to explain why this is, right? Because think about it. It's like a 50-50 shot, yes or no. We've got to try and explain it. So when you have a dilation preserves angle measure. So I'm going to start by writing that. I'm going to say dilations preserve angle measure. And I can say, so the triangles are similar by angle similarity theorem. There are different things you could write here. You could talk about how the sides are proportional because they were all doubled. Side, side, side is another similarity theorem. You could talk about corresponding angles being congruent and parallelism being preserved. You have a lot of options here, but the idea is that we want to say yes, and we also want to give some sort of explanation as to why. Okay, let's look at number 33. It's a proof. In the diagram below, triangle ABE is congruent to triangle CUD, and we want to prove that triangle AFD is congruent to triangle CFE. So I've already gone ahead and set up my two-statement reason columns, and I've copied in the givens. Since we are given that two triangles are congruent, let's see if there's anything that's in those triangles that are also in the triangles we want to prove are congruent. So if I look at them, I can see that, for instance, angle A and angle C are in, for instance, triangle ABE. Angle A is in that triangle, and it's in triangle ADF. So I'm going to say that angle A is congruent to angle C by CPCTC. And I'm going to go and mark those in my picture. And then let's see if there's anything else where basically there's something from the given congruent triangles that are in our new congruent triangles, or the ones we're trying to prove are congruent. So if I look at this, I notice that, or I can tell that like AB and BC are going to be congruent, right? Because those big triangles are congruent to one another. If you need to, you could always separate these triangles if it's helpful for you to look at them, the big triangles, so that they are not overlapping here. You could always separate them, and I'll copy over all of the points. So I know that AB is congruent to CB. However, that's not a side of the new triangles. It's more than the side, right? If you guys see what I mean by that, if I zoom in here, I know and I can explain that AB is congruent to CB because of CPCTC. But I need AD and CE. I need the smaller pieces of that. So since these are part of those segments, we could use the idea of segment addition to work through this, because we also know that DB and EB are congruent, okay? And if you look at this picture over here, you can see how that's going to be true for each of the triangles, okay? And I'm just realizing this should be an E down here, okay? All right, let's write what we know about the CPCTC. So I know that AB is congruent to CB. Those are my pink pieces. And I also know that DB is congruent to EB. All of that is because of CPCTC. Okay, so I know these big two pieces, and I know my two green pieces are congruent. Well, think about it. If the pink pieces are congruent and the green pieces are congruent, those blue pieces must be, right? Because it's just the difference between them. So I'm going to use segment addition in order to talk about this. And this can get a little confusing, but always try and write it out and explain your ideas if you're unsure of how to write it in a more technical format. So I'm going to say that AD plus DB is congruent to CE plus EB. And that's by the segment addition postulate. I'm taking congruent segments and adding them to congruent segments. And if you don't know the name of the postulate, again, you could say, explain it the way I just did. Basically, when you add congruent segments to congruent segments, their sums are congruent. Now, using this train of thought, AD is going to be congruent to CE because we're basically subtracting out DB and EB from them, right? We're taking away those green pieces. So I'm going to call that the subtraction postulate. You could talk about it as segment subtraction as well. So that being said, in our picture, I'm going to mark off that AD and EC are congruent. So now I have two things marked off in those triangles. I am going to go to this picture here, and I'm going to, just for the sake of not cluttering this picture, I'm going to erase anything that we don't need anymore. And remember, we're just trying to prove that triangle ADF and triangle CFE are congruent to each other, and I have two things marked off in each. I can get a third thing through these vertical angles. So I'm going to write for line 5 that angle AFD and angle CFE are vertical angles. And that's because intersecting lines form vertical angles. And now in line 6, I can say they're congruent. You can merge these two lines together as long as you don't omit any information, that's fine. All right, we now have 3 things marked off in each triangle, so I can prove these triangles are congruent. So my prove statement, and I'm going to look at the picture and see what method I can identify, and that's angle, angle, side is congruent to angle, angle, side. Okay, number 34, a cargo trailer pictured below can be modeled by a rectangular prism and a triangular prism. Inside the trailer, the rectangular prism measures 6 feet wide by 10 feet long. The walls that form the triangular prism each measure 4 feet wide inside the trailer. The diagram below is of the floor, showing the inside measurements of the trailer. Okay, so they give us this real life picture, but then they give us kind of like the more geometric one off to the side. If the inside height of the trailer is 6.5, what is the total volume of the trailer to the nearest cubic foot? So let's basically find the area, or excuse me, the volume of the rectangular prism. Let's find the volume of the triangular prism, and let's add them together. So for the rectangular prism, we can think about that as length times width times height. So 10 times 6, and it gives us that 6.5. For the triangular prism, we have to think about this one a little bit more here. We've got to say, well, how can I find the missing values here? And by the way, if you go to your reference sheet, the formula is capital B times H for any type of prism. Area of the rectangle's base is length times width. That's where the 10 times 6 comes from. And if I think about it here, the area of the triangle is what I need to find for B. And then the height, we know is 6.5 again. Okay, so I'm basically looking, can I figure out the area of the base for this triangle? All right, if we examine that picture a little bit closer here, I'm going to zoom in. Notice the 6 over here. Now I know that this is also 6 feet. Since that was a rectangle, opposite sides of a rectangle are congruent to one another. And I'm looking for basically the height of this triangle. I'm looking for this. So let's split this 3 and 3. And let's do Pythagorean theorem to figure out what this measurement is. So I have 3 squared plus, let's say, b squared equals 4 squared. 9 plus b squared equals 16. B squared is 7, and b is radical 7. Okay, so I know that this value, this height, is radical 7. So if I want to find the area of this triangle, it would be 1/2 the base of 6, the height of radical 7. So I'm going to plug that information in here. And we're going to round all this to the nearest cubic foot. So we're going to start just putting all of this into the calculator. So the first part was 10 times 6 times 6.5. Plus, I have 1/2 times 6 times radical 7. And then I'm going to multiply that all by 6.5. And when we get our answer here, we're rounding to the nearest cubic foot, and that is going to give us 442 cubic feet. All right, last problem is our only 6-point question, our part 4. It tells us the coordinates of vertices of triangle ABC are 1, 2, -5, 3, and -6, -3. Prove that's isosceles. It says the use of the axes on the next page is optional. So if you find that you're a very visual learner, you might want to go ahead and plot them. Or if you're just sitting there with extra time, since it is a 3-hour exam, and you want to check your work, graphing is a great idea. So I'm going to go ahead and graph and plot. A is 1, 2, B is -5, +3, and C is -6, -3. And I'm going to make nice straight lines connecting the 3 vertices of the triangle. All right, so we want to prove that it's isosceles. We could probably guess by looking at the picture which sides look isosceles to me, or which sides look congruent. A, B, and B, C look congruent, but we're going to show that. Okay, so the way we can show things are congruent is by using the distance formula. So I'm going to find the length of AB. Distance formula is subtract the x's squared plus subtract the y's squared. And when I do that, I get radical 37. And now I'm going to find the length of BC. When I find the length of BC, subtract the x's squared, subtract the y's squared. I also get radical 37. Now I know this triangle is isosceles. If you wanted to and you didn't graph and you weren't sure, you could add in the extra information and find the length of CA. That's not a problem to have extra correct work. But I'm going to say that triangle ABC is isosceles since 2 sides have the same length. Anytime you're doing this type of proof, it's called a coordinate proof, you need words in there. You need to write a sentence. All right, state the coordinates of point D such that quadrilateral ABCD is a square. All right, so I'm going to go to my picture here, and remember before we said the graph was optional, but to me, this is why the picture is so helpful, because I can use it to figure out the coordinates that would make this a square. So I know a couple of things. That I know that in a square, all of the sides are equal. I also know opposite sides are parallel. So if sides are parallel, that means their slopes are the same. So I see that from B to A, I'm going down 1 and over 6. So if I do that with C, go down 1 over 6, here's where point D lands. And that looks like it has the coordinates 0, -4. So those are our coordinates of D. Now we've got to actually prove it's a square. So when we're doing a proof to show that it's a square, there are many different things you could do. You could show that consecutive sides are perpendicular and the diagonals are perpendicular. You could show that all 4 sides are congruent and that the diagonals are congruent. That's the route that I'm going to actually pick here. Or you could do a combination of a few different things. So I like to personally use distance. So if I was proving something is a square with distance, I would want to show that the 4 sides are congruent and that the diagonals are congruent. So to show it's a square using the distance formula only, I'm going to show the 4 sides are congruent, the diagonals are congruent. So let's list what the 4 sides of the square are. So there's AB, BC, CD, and DA. We have already found in this problem that AB is radical 37 and that BC is radical 37, so I don't need to recalculate them. And the diagonals in this problem are BD and CA. All right, so let's see if this works out. Remember, it should. It's not a question. It's not saying, is it a square? We should be getting correct answers here that quote-unquote match. So when I find the length of CD, I should definitely be getting radical 37. All right, so D, remember, is 0, -4, and that's what we found in that previous part. All right, let's subtract the x's. So C is, I'm going to write the values on this page, by the way, so you guys can see them. A is 1, 2, B is -5, 3, C is -6, -3, and D is 0, -4. So rather than scrolling back and forth, here are the 4 coordinates that we're looking at. All right, so for CD, subtract the x's, subtract the y's, and when I type that into my calculator, yes, I get radical 37. If you're not sure how to type that into the calculator, here's what I'm doing. I'm typing in everything except the radical. When I hit enter, you see I get 37, and then I just put the radical back around it. All right, for the last side for DA, subtract the x's, subtract the y's, and that will be radical 37 as well. All right, let's move on to the 2 diagonals. Subtract the x's, subtract the y's. Now, when you're doing this and you're finding the length of the diagonal, we should not get radical 37 now. The diagonals are not equal to the sides. They're just equal to each other. So I'm going to type this in. I'm going to have 0 minus -5 squared plus, when I subtracted the y's, I got -4 minus 3 squared, and I got radical 74. Now if I find the length of CA, subtract the x's, squared, plus subtract the y's, squared, and I'll put that one in my calculator. Again, I'm just putting everything but the radical in the calculator. If I put the radical in, I'm going to get a decimal. It's not that that's wrong. I just would rather not work with the decimal here. And I got radical 74. So I'm going to say that ABCD is a square because, remember, we always need a sentence. All 4 sides are congruent. And the diagonals are congruent. Both of those parts are key. You need both of them. If we just said all 4 sides are congruent, that could be a rhombus. So we do need to definitely add in this extra piece about the diagonals as well. Make sure you check out the rest of the videos on my channel. You'll see many more Regents exams for geometry and their solutions.